inconvenience and the disruption, it was not expected. So I will try to be fast to compensate for the loss of that time. I would like to thank Professor Zhang Li and Professor Sergey Ev for the invitation and for the organization. And I would like to talk about optimal control of Markov QGEM processes. In our community, the more popular terminology is continuous time Markov decision process, or MDP in continuous time. And I would like to start with description of the model of discrete time MDP and the relevant optimality results for two reasons. One, I would like to rigorously introduce the continuous time problem as a specific discrete time MDP. And two, I would like to establish similar optimality results for continuous time problems as those for discrete time problems, which were known in the literature. So, yes, so discrete time MDP, you have a discrete time Markov chain, and you can control its transition probability. And at each time step, depending on the state and the action you selected, some losses are incurred. So you have the following system primitives. X is the state space, A is the action space. We assume they are borrow spaces, or Rn for simplicity. And then this transition kernel is just a stochastic kernel from X times A to the set of probability measures on the borrow sigma algebra of X. And then I assume all the cost functions or loss functions are measurable and positive, taking non-negative values. And strategy specifies the selection of actions at each time step. And it is given by a sequence of stochastic kernels, which can depend on the current time step and also all the available history, constituted too by the past states and actions. If there is no dependence on the current time and the dependence on the history is only through the current state, then the strategy is called stationary. And of course, the stationary strategy is identified with the stochastic kernel. And in case the stochastic kernel degenerates and is concentrated on the value of a measurable mapping from X to A, then this strategy is called deterministic stationary. For the problems considered in this talk, deterministic stationary strategy actually will not appear because it is not sufficient for the optimality purpose. And so we are interested in the following problem, which was well documented in the literature. So we would like to minimize the expected total on discounted costs with respect to L0 and subject to constraints on the values of other expected total costs being not too big. And one of the first people who considered such problems was Yefim Fried in 1972. And he considered problems with discounting, and the presence of discounting makes the situation much simpler, I can see. So in what follows, whenever I talk about constraint problems, I always assume there exists a feasible strategy with a finite value because I'm interested in the existence of optimal strategy. So I mentioned one recent breakthrough regarding this problem, which says the following. So under some conditions, this discrete time MDP is equivalent to a static optimization problem. And so one can arrive at this problem very easily. So if one introduces the so-called occupation measure, defined as the expected total state action frequency, then this and you integrate the cost function with respect to the occupation measure, you get the total undiscounted cost. So, so this eta, you can replace this eta by the so-called occupation measure, and occupation measure satisfies this so-called characterization equation. And then this inequality corresponds to the constraints on the values of other expected costs. And also under this condition, under this condition W, there exists an optimal stationary strategy. So what is untrivial is that in general, you can have phantom solutions to this characterization equation. And therefore, in general, without this condition W, the MDP is not equivalent to this static optimization problem. And what does this condition W say? It says the action space is compact and the transition probability is weakly continuous in XC, which means that for any bounded continuous function on X, you take integral with respect to this P dy given XC, then the integral is continuous in X and A. And also all the loss functions must be low semi-continuous. And so we would like to establish similar results for continuous time MDP with both gradual and impulsive control. Oh, by the way, so this equivalence or between the discrete time MDP and this convex program or linear program is called linear programming approach or convex analytic approach for MDPs in the literature. So, okay, what is the continuous time MDP I have in mind? So consider continuous time Markov chain, and you can control its transition rate or local characteristics by the so-called gradual control. And in addition, you could control the state of the process instantaneously by the so-called impulsive control. So we admit both types of controls in the model. And therefore, the system primitives of the continuous time problem looks like the following. Yes, so again, we have a borrow state space. And now we have two action spaces. One is for the gradual control, e.g. the other AI is for the impulsive control. We assume AG and AR are disjoint borrow subsets of a common borrow space, which is given by the union of these two action spaces. And this assumption is made without loss of generality. Then the transition rate is what gradual control X. So it is given by a signed kernel from X times EG to X, such that the value of this kernel is non-negative if this gamma does not contain this X. And if you replace this gamma by capital X, then the value is 0. We denote QXA as the jump intensity when the current state is X and under the action A. And we assume the jump intensity is uniformly bounded with respect to A, but we do not require it to be bounded with respect to the state. And finally, Q-theta denotes the post-jump measure, whose meaning is either already clear or will be made clear in 2 slides. Then we have a stochastic kernel capital Q from X times AI to X. This capital Q describes the distribution of the new state after immediately one applies an impulse. So if the current state is X, the action is B, impulse action is B, then the state following applying this impulse follows the distribution given by this capital Q. And finally, we have the loss functions, cost rates. So 2 cost functions. So one for the gradual cost rate, which is accumulated over time, and the other one is for the cost incurred whenever an impulse is applied. So now let me describe what is meant by relaxed control function. So I would like to recall some known effects, general effects. So consider borrow space Y, and then consider the space of borrow measurable mappings whose domain is the set of positive real numbers and whose values is in this borrow space Y. And then one can introduce a suitable sigma algebra on this space to make it a borrow space. This was one a suitable sigma algebra is generated by functions of this form. And this is a classical result of USKH in 80. And in our context, this Y will be equal to the space of borrow probability measures on AG. And we even use a new notation for this set. And the new notation is calligraphic R because any element of this set is understood as a relaxed control function. So for any element, for any relaxed control function from this calligraphic R at time t, this rho t is the probability on AG. And one can understand it as a distribution of the action at time t under this relaxed control function. So with this sigma algebra, I just want to assure you that all the functions with arguments involving this row below are jointly measurable in their arguments. And I need this borrow space, I need this measurability in order to formulate the continuous time problem as a specific discrete time MDP, which was described in the beginning of this talk. So now I verbally describe the system dynamics. So at the initial time 0, with the initial state x0, the decision maker selects a triplet. C0 hat from 0 to infinity, B0 hat from AI, and rho 0 from calligraphic R. The interpretation is as follows. So C0 hat is the time duration you would like to wait before you apply the next impulse, provided that there is no natural jump taking place before them. And B0 hat is the next associated impulse. And the rho 0 is a relaxed control function you would like to use during the next time, during the next sojourn time. So here I want to mention that C0 hat can take value 0. This means we allow multiple simultaneous impulses at any time moment. And when C0 hat is equal to infinity, it means you do not apply any impulse until the end of the current sojourn time. So that time until the next natural jump follows the exponential distribution, non-stationary, with the rate function given by this integral, which is denoted for abbreviation and brevity as this, qx0 of rho t0. And this notation is used for any functions whose argument is a. If A is replaced by a corresponding probability distribution, then the meaning is the integral with respect to A, in A with respect to the distribution. So if by time C0 hat, there has been no occurrence of a natural jump, then the first sojourn time is C0 hat. That means the sojourn time is ended with the so-called active jump caused by an impulse. And at that time, the impulse B0 hat is applied, and the next state X1 follows the distribution given by this kernel capital Q. On the other hand, if the first natural jump happens before C0 hat, say at some T1, then the first sojourn time is T1. And the next state X1 follows the distribution given by the ratio of the post-jump measure against the jump intensity at X0 on the rho 0 at T1. So a decision epoch occurs immediately after a sojourn time, and at the next decision epoch, the decision maker has to select next triplet, so on and so forth. So apparently this is the sequential decision-making problem, and we would like to formulate it in the framework of discrete time MDP, which is a powerful and useful framework for handling such decision-making problems. And the MDP formulation is as follows. So the system primitives. Okay, so you have the state space, which is X hat. And I mentioned that this, okay, any state in this MDP has two coordinates. The second coordinate recalls the state of the continuous time model, and the first coordinate recalls the most recent sojourn time. In other words, the sojourn time leading to the current state. And if the sojourn time is if the sojourn time is infinity, then it means the process is over, and we put the state as x infinity, which is the symmetry, costly symmetry point. So I regard this pair, this point, as an isolated point of this x hat. The action space is just the space of the triplet described in the previous slide, given by the product of these three spaces, and transition probability is just defined in terms of the previous description. So let me repeat. Here, the first term corresponds to that the natural jump takes place before C hat, and therefore the next state distribution is determined by post-jump measure. And the last term here corresponds to that the current sojourn time is ended with an active jump. So this exponent is probability that no natural jump takes place by C hat. And in this case, the next state distribution is determined by this capital Q. And the term in the middle of these expressions corresponds to that you have infinite sojourn time. And if you start with this symmetry, you remain there indefinitely forever. And finally, we have the loss functions. The loss function is given by the accumulated total cost over the current sojourn time. And here it depends on the current state of this discrete time MDP action and the next state of this discrete time MDP. This is because the first coordinate T here actually recalls the current sojourn time. So I can take this integral over the current sojourn time. So over the interval from 0 to T here. This is one of the reasons why I have additional coordinate in the state of the discrete time MDP. And in case the current sojourn time is ended with an active jump, then you have to add additionally the cost from applying an impulse P hat. So this is the MDP formulation for my continuous time MDP problem. And the strategy in the gradual impulsive control model, which is denoted as choreographic M, which specifies how to select those triplets. So it is given by a sequence of pairs. So sigma n0 describes or specifies how to select the C hat guys and B hat guys. And depends on the current step and depends on the history available. And the history is in this form, but remember, X hat guys are the states in this discrete time MDP. So each of them has two coordinates, which recalls both the state and the sojourn time in the continuous time model. Also this F hat N is a matchable mapping from H N hat, C hat, B hat to the set of relaxed controls, which specifies how to select a relaxed control function to be used during the next sojourn time. So here is the description under a strategy. Having in hand the history H n hat, decision maker firstly selects C n hat B n hat according to this stochastic kernel sigma 0 n. After that, he chooses the relaxed control function rho n as given by f n hat, h n hat, c n hat, b n hat. Just like that. Of course, each strategy in model calligraphic M defines a strategy in the underlying discrete time MDP. So everything is now completely embedded in a discrete time MDP, and we consider the following gradual impulsive control problem. We want to minimize the expected total cost subject to constraints like this. So constraint problem. Okay, so literature. Yes, so what was described covers two special situations. The first special situation is when you only have purely impulsive control, no gradual control. A particular example is the so-called optimal stopping problem. Another special case is when you only have gradual control, no impulse control. And those models are often called standard CT-MDP, and we will call them standard CT-MDP in this talk. They both have their own literature, and I will not mention them here. I only mention the most relevant ones to this talk. So Yushkevich in 83, 88, 90 considered gradual impulsive control problem. He considered problem with single objective, and he analyzed the optimality equation. This is not the target of this talk. And in close relation to this talk, there is a series of more recent works by Francois Dufour and ArXiv, and they consider discounted problems. And discounted problems are special case of total undiscounted problems, and they follow a direct method. Different method, direct method means making use of Jenkins formula, which involving in identifying the domain of extended generator, which usually imposes restrictive conditions on system primitives. And here what we do, we are based on the reduction of the gradual impulsive control problem to an equivalent standard CTMDP with gradual control only. And in turn, this standard CTMDP can be reduced further to a discrete time MDP with the same action space. So I just want to mention that the MDP which we use to formulate the continuous time problem is with the more complicated action space as compared to the continuous time model, because it involves the space of relaxed control functions. That is a more complicated object, and it is not so convenient to work with it. So let me now describe what is known and relevant for standard CTMDP. So in standard CTMDP, as I said, there is only gradual control. There is a old history of studies on this problem. One of the first work comes from Markov in '66, and the most recent work probably is by Eugene Feinberg and Shleyev, Albert Nikolaevich in 2021, and there are many works in between. I don't want to mention them. So because there is no impulse control, the model has the following system primitives. And the model is denoted as calligraphic MGO. This notation will be used very often. So state space, action space, and only the transition rate and only the cost rate, no impulse, nothing. And the GO stands for gradual only. So this is just to emphasize the model being considered. And then a strategy in standard CTMDP is just given by a sequence of functions which specifies how to select relaxed control functions. So if the current history is Hn, then Fn bar of Hn is relaxed control function, which depends on T and takes values in the space of probability measures on A. In case there is no dependence on this T, that means the relaxed control function is a constant function. And in case there's no dependence on this N, and the dependence on history is only through the current state, then the strategy is called stationary. And of course, each strategy is identified with the process pi dA given omega t. Omega is the element of the canonical sample space. And so this process is defined as Fn of Hn sub t minus Tn of dA. If this t, the current time, is between Tn and Tn plus 1. So Tn is the time of the nth jump moment. Tn plus 1 is the time of the n plus first jump moment. So this is just a notation really, because with this notation pi, I can write down the performance measures more compactly. So for standard CTMDP, one can consider total undiscounted problem. So this is the expected total undiscounted cost, then constraints of similar type. So XT is the state process. And this is a pure jump process. So if the current time is between the nth and n plus first jump moments is equal to xn, not changing between two jump moments. And here we do not exclude the accumulation of jumps. So it is possible that explosion time is finite. We do not exclude the situation, but we consider the problem up to explosion. That means if t is greater or equal to t infinity, then I put the process state equal to the symmetry point x infinity. So if one follows a direct method, in most of the situations, one imposes conditions which a priori exclude such situations to take place. And then I want to mention discounted problem. So if here you have the additional discounting with alpha positive strictly, then the problem is called discounted problem. If alpha is 0, of course, you have undiscounted problem. But it turns out that alpha strictly positive really makes everything simpler. For discounted problem, there is a nice observation of Eugen Feinberg, so which says that the discounted problem is equivalent to the following MDP problem. So this MDP problem has the same action space as the original action space in the continuous time model. And this MDP is just like the alpha jump chain obtained from the alpha jump chain of the continuous time Q jump process. And but we are interested in the undiscounted case corresponding to alpha equal to 0. So when alpha equal to 0, you just put alpha 0 here, here. And if you accept 0 divided by 0 equal to 0, this is again a legitimate MDP problem. And you want to ask whether this equivalence is still valid. And the answer is negative in general. This actually can be seen from a simple example. Oh, by the way, if alpha is equal to 0, then this MDP is really the embedded chain. So this example has two states, 1 and 2. The action space is from 0 to infinity. We start with initial state 1. And from 1, you can only go to 2. And state 2 is absorbing costless symmetry. So the jump intensity at state 1 when the action is A is given by E2 minus alpha. And the jump intensity at state 2 is 0. And the cost rate at 1 is the same as the jump intensity, again, E2 minus A. And there is no cost when the current state is 2. Then consider a simple strategy which takes action equal to the current time t. And then you can calculate the jump intensity under this control pi. So it's just equal to E2 minus t, which is the same as the cost rate under this strategy. And then we calculate the expected total undiscounted cost under this strategy. So because there is only one subjoin at most, it is enough to replace this interval from 0 to infinity as from 0 to t1, the first jump moment, because after the process goes to state 2, there's no further cost being incurred. And over this interval, the controlled or the cost rate under control is given by E2 minus t. So if this t1 is equal to infinity, then this integral is equal to 1, the expectation is equal to 1. But what happens is that this t1 is finite with strictly positive probability, meaning that this expectation is strictly smaller than 1. On the other hand, for the embedded chain, remember the cost function is given by this ratio. This ratio is always equal to 1. And the transition probability from 1 to 2 is always equal to 1. So under each strategy in the MDP model, discrete time, the expected total cost is always equal to 1. So for any strategy is equal to 1, meaning that any strategy is optimal for discrete time MDP, but the value is different from the value of the continuous time MDP. So this means in general, the reduction when alpha equal to 0 may be not valid. And the first observation we have is that under some conditions, this reduction is still applicable. And yes, so what are these conditions? This condition is similar to condition W for discrete time MDP. Action space is compact. This post-jump measure satisfies certain failure property, and the cost rates are lower semi-continuous. So also under this condition, WGO, there is a stationary optimal strategy. We will use this result to deduce the existence of stationary optimal strategy for gradual impulsive control problem ultimately. So now I talk about, okay, now I go back to the original problem, model M, and I claimed that it can be reduced to a model with gradual control only. So the induced gradual control model has the following system primitives. So they are defined in terms of the primitives of model choreographic M, the original model. And I just give terminologies which will be used in the next few slides. So a strategy in a model is said to replicate another strategy in a possibly different model if their performances are the same in their respective models. And then we see one model is reduced to another model if any strategy from one is replicated by a strategy from another one. So these are just the terminologies. Then the first observation is here. So each strategy in the gradual impulsive control problem can be replicated by a strategy in the induced standard CDMDP. For the opposite direction, let us now tentatively impose the following condition in blue, which says that at any state X, the jump intensity is separated from 0. And under this condition, each strategy in the induced standard CTMDP can be replicated by some strategy in the original gradual impulsive control problem. That means under this blue condition, the original model is reduced to a standard CTMDP. And what we can see a bit more is as follows. So under the blue condition, we have the following sufficient class of strategies for the original problem. which says that we can concentrate on strategies with some kind of low-cost stationarity. And so what I mean is as follows. So if you look at the last line here, so the dependence on history is only through the current state. And also the relaxed control function is constant. And but you have to remember this n, this dependence on n is presence. And similarly, on the two lines above, there is dependence on this n, the current step. So this is important. And what these first two lines say is as follows. So firstly, if you put this dB hat as AI here and here, you add these two lines together, you get 1. Because this stochastic kernel will be equal to 1, and you have 1 minus mu n plus mu n equal to 1. And this means you either apply impulse immediately after a sojourn time, or you do not apply it until the current sojourn time is over. So this is the form of sufficient class of strategies. Okay. And what we will explain now is how to remove this blue condition. Oh, I also want to mention that the sufficiency result is is true only with this blue condition. Without this blue condition, the sufficiency result does not hold. But it turns out that without this blue condition, it is possible still to reduce the original model to a standard CTMDP, and this is done by introducing the so-called pseudo Poisson-related strategy and Poisson-related strategy into the models under consideration. So I will describe how pseudo Poisson-related strategy works, and then I give the formal definition. So fix lambda positive, just a constant. And I introduce this notation lambda bar of A. So, okay, here I'm talking about model MGO. So this is the induced standard CTMDP by the original model M. So this is just a function. It is equal to 0 if this A is not in AG. That means if this A is from AI, and otherwise it is equal to the constant lambda. Very special function. And okay, so suppose for any n we have a sequence of stochastic kernels. Okay, P bar nk. So so this lambda and these sequences of stochastic kernels will define a so-called pseudo Poisson-related strategy. So it works like the following on the such a pseudo Poisson-related strategy. So at the initial time, with the initial state x0, you generate a random variable phi 0, 0 according to p00, this stochastic kernel. X0 is known, so this is just a distribution. And based on this phi 0, 0, you generate psi 1, 0 according to this exponential distribution. If this lambda bar is equal to 0, then this is infinity. And then you use this phi 0, 0 as your action control during the interval from 0 to the minimum between T1, the first natural jump, the first jump moment, and this psi 1, 0. Of course, two things can happen with respect to this infimum, this minimum. Okay, so if this psi 1, 0 is smaller than T1, then you generate another random variable phi 1 of 0 according to this stochastic kernel P bar 0, 1. And given this value, you generate psi 2, 0 according to this distribution. And then you use phi 1 of 0 as the action during this interval. So And if this is not the case, if phi1 of 0 is greater or equal to T1, that means this minimum is equal to T1, then you produce phi 0, 1 using P bar 1, 0. This is different from P bar 0, 1. So you use P bar 1, 0. This stochastic kernel at x1. X1 is the state after the first jump. Okay, and given this phi 0, 1, you generate psi 1, 1 according to exponential distribution with parameter depending on phi 0, 1. And you use phi 0, 1 as the action during the interval from T1 to the minimum between T2 and T1 plus psi 1, 1. So on, so forth. So this is how pseudo-Poisson related strategy works in a model MGO. I will give a picture to illustrate this in the next 2 slides. So I can give a formal definition of pseudo-Poisson related strategy. So that means I will define a common sample space where all these phi guys and psi guys live. So this involves notations. Psi GO. Psi GO is just the, you can understand it as the canonical sample space of a marked point process, and with marked space being A. And the generic notation for an element in this set is Xi. This Xi is a sequence of pairs. And so psi n is from 0 to infinity, and alpha n is in this A. And then all those psi guys and phi guys mentioned in the previous slides are just coordinate random variables. So they actually define marked point process. Now the formal definition of Poisson-related strategy in model MGO, the induced model. So it is given by a sequence of stochastic kernels on the space of XGO. So satisfying the following conditions. So note that given this X, this distribution is the distribution of a marked point process. So we require the distribution of that marked point process to be such that psi 0 is always equal to 0. And psi 0, psi 1, phi 0, psi 1, phi 1, psi 2, these pairs, they are mutually independent and satisfying these two conditions, as was described in the previous slide. So phi k guys are produced according to this stochastic kernel, and given the value of phi k, psi k plus 1 follows exponential distribution with rate given by lambda bar of phi k. So this is the formal definition of pseudo-Poisson related strategy in model MGO. And we can similarly introduce the so-called Poisson related strategy in the original model M. Oh, before I do that, I just give this illustration. So in this picture, as I said, so, okay, T1 is here. This is the first jump moment. And at the initial time, you generate, I call it alpha 0 according to P00. And based on alpha 0, I generate psi 1 of 0 following this exponential distribution whose rate is lambda bar of alpha 0. And use this alpha 0 over this interval because T1 is beyond the end of this interval. And at this point, you generate another, I call it alpha 1, using P01. And based on alpha 1, you generate psi 2 of 0. And you use alpha 1 over the next time increment of psi 2 of 0. And at this moment, you generate alpha 2 according to P02. And you generate psi 3 of 0. And in this picture, this psi 3 of 0, goes beyond T1. So you have to stop at T1. You use alpha 2 over this small interval up to T1. And at T1, you have to restart. That means after each sojourn time, you generate a marked point process based on which you control your process. And this is different from relaxed control. So here you use the same action for a certain period of time, and then you switch. And the time at which you switch is random. Okay, so one can similarly define so-called Poisson-related strategy in the original model. Just difference is that here instead of A, you have a G. And another difference is that now this psi 0, this psi guys and phi guys, they really constitute two a standard Poisson marked point process with marked space AG. Originally, it's not Poisson, but now it is really Poisson. The distribution of the psi guys are really standard exponential distribution with rate lambda. And also, in addition, you have to have some stochastic kernel which selects the C hat guys and B hat guys. And you can depend on this Xi. This Xi is the marked point process you generate after each sojourn time. So we call these pairs a Poisson-related strategy in the original model. And it turns out that these two strategies are really useful to establish the reduction result, which is described now. So the observation is that each strategy in the induced model can be replicated by a pseudo Poisson-related strategy in the same model. And each pseudo Poisson-related strategy in the induced model MGO can be replicated by a Poisson-related strategy in the original model. And in turn, each Poisson-related strategy in the original model can be replicated by a strategy, standard strategy in the original model. And then we recall that each strategy in the original model can be replicated by a strategy, standard strategy in the induced standard CTMTP. So this completes the loop. The gradual impulsive control model can be reduced to the model MGO with gradual control only. So I now draw a conclusion with respect to the optimality results very fast. So which says under some conditions there exists stationary optimal strategy. So here we have global stationarity. So there is no dependence on this N. So and it only depends on the current state. So no dependence on this N. So there exists such a strategy is called stationary, and there exists a stationary optimal strategy on the condition W hat. W hat is just the conditions on the system primitives under which WGO for the induced gradual control model is satisfied. And last question, how to obtain stationary optimal strategy? It can be obtained in theory by solving a convex program. Okay, I just showed the look of this convex program, skipping the details. What happened? Yes, so So yes, so all right, okay, okay, firstly, for some there is a specific subset R of the state space. Outside this, R things are trivial. So just I do not define this R, but there is a specific subset R, and you consider this convex program in the space of sigma finite measures on R times A. So again, this integral here corresponds to the total cost, and similar integrals correspond to the constraints. And then you have some characterization equation, and this one just comes up automatically. I'll emphasize that this is a convex program in the space of sigma finite measures, not finite. One has to deal with sigma finite, but infinite measures. If one solves this convex program successfully, then one can produce optimal strategy for the original problem. So firstly, that convex program really has a solution under condition W hat, C nu star. Based on this nu star, one can produce the optimal strategy. And I only mentioned the first step. So first step is that you should disintegrate this nu star with respect to its marginal. And by doing so, you obtain a stochastic kernel from R to A. And this disintegration is possible because the measure is sigma finite. If the measure is arbitrarily infinite, then this is the problem. And then you complement the definition of this stochastic kernel from R to the whole state space. This is just something very simple to do. This F star is a specific mapping, but I do not describe it here. And after that, you start with this stochastic kernel. You can produce optimal stationary strategy for the original gradual impulsive control problem. So I omit